Hey class, Mr. Moyden here with a video on a tangent line approximation using that concept of the fact that a differentiable curve is locally linear so that the line tangent to the curve is a very good approximation to its behavior. We can use that description to help us find values for what is otherwise very difficult to do without a calculator, like for example the cube root of 7.2. So the first thing to identify is the real function that we're describing here is the cube root of x, right? Some unknown value, which in this case happens to be 7.2. So right away you should notice that the number I've given you should be fairly close to one that's pretty doable, like a known value, so to speak. And hopefully you recognize that this function is, when you plug 8 into it, which is pretty close to 7.2, you get an output of cube root of 8 is 2. 2 times 2 times 2 is 8. So this is sort of our fixed value, and this is our function that generalizes this. Now, just to have a picture for this, roughly speaking, I believe the cube root function looks something like this. And 8 would give us a value of 2. And since plugging this number in is not really feasible in terms of how to actually get an answer, we can use the line tangent to the curve, which I did a terrible job drawing, but you get the idea, where if you zoom into it, you would see the curve, and you would see the point 8, 2 that it passes through, and you would see a tangent line that very closely approximates the behavior in that general vicinity. The further away you go, of course, it has nothing to do with the function, but very close to it, it does. So we're going to use that we're going to leverage this approximation ability to allow us to figure out the value of this to pretty close accuracy. So we need to find the equation of that tangent line. We need to essentially linearize this curve. So the function itself is the cube root of x, which in terms of making it ready for calculus is x to the 1/3 power, right? The equation of a tangent line, just in general, is going to be y minus the y value equals the slope, x minus the x value, right? So that's the equation of this line, or really of any line. We already know our x1 and y1. That's our sort of fixed value that we identify as being close to what we want. So right away we know our answers, or our tool for finding our answer is going to be y minus 2 equals some unknown slope of the curve at that point, x minus 8. Right? So what we got to figure out is what is the behavior of the curve. Is it increasing or decreasing? And if so, how much at the point in question, which is around 8, 2. So to do that, long story short, we need to take the derivative. So if, let me use an alternate notation here, if the function is y equals x to the 1/3, then dy dx using the power rule would be 1/3 x to the 1 less than 1/3, 1/3 take away 1, or 1/3 take away 3/3 is negative 2/3. And in the past, an answer like this is sufficient, or it's suitable, but it's not really useful for plugging numbers into. It's mathematically correct, but it's not exactly user-friendly. So we're going to make it user-friendly. I'm going to leave the 1/3 as is. X to the negative 2/3, make that positive by putting it underneath the 1, just by the definition of a negative exponent. So that becomes x to the positive 2/3. I'm just going to combine fractions here to make this a little easier. So multiplying the tops and the bottoms, I have 1/3 x to the 2/3. And if you recall, the original function was a radical function, cube root of x. And this is not a radical, so I can use this technique of making a fractional exponent in the opposite direction to make this back into a radical again. So how am I going to do that? Well, one way to think about this is it's x to the 1/3 quantity squared. Because if you actually use the properties of exponents, you'll see that these and this is the same, right? So that furthermore, using the fact that this is really cube root of x, makes our derivative, not our answer, but our generator for slope, to be the cube root of x quantity squared. So that's really the useful form of the derivative. Okay? So let me just write that separately here. dy dx in general for this function is the 1/3 times the cube root of our input squared. Well, the point in question was 8, right? We need to find the slope, and you can kind of guesstimate it's going to be fairly shallow, but positive, at that point of 8, 2. So we're going to plug 8 in there, and the notation for that looks something like this, just so you're familiar with it. dy dx evaluated at x equals 8. means we have 1 over 3 cube root of, well, x is 8, so I'm going to take cube root of 8, and take that result and I'm going to square it. Well, cube root of 8, if you recall, is 2, so 2 squared is going to give me 4, times 3 will give me 12. Make sure I did that right. Cube root of 8 is 2, squared is 4, times 3 is 12. So indeed, the slope is positive, but fairly shallow. It's not very steep, of 1/12. So now we have our m value. So the equation of this line, specifically, is y minus the y value that we used. Now we have our slope, mx minus the x value. So this is a very good approximation. In other words, y equals cube root of x is very, very close to this when x is very close to our fixed point of 8. And, 7.2, not bad, pretty close. Not the closest possible number, but not infeasible either. So now we're going to plug, because we can't really figure out how to plug 7.2 in there. That's the whole crux of the problem. We're going to plug 7.2 into here. So y minus 2 equals 1/12. 7.2 take away 8. Okay? Well, 7.2 take away 8, let's see, that's going to be 1/12, it's going to be negative 0.8, 8/10, right? If I did that right. And that's y minus 2. Well, let me write this as a fraction here. We have 1/12 times negative 8/10. That's literally how to read that. Y minus 2 equals that. And if I combine fractions here, I have negative 8 over 120, which can be reduced, but for our purposes, it's okay the way it is right now. And we have that equals y minus 2, which is all down here because I didn't scroll the paper up. Sorry about that. So it's just describing how to combine fractions. And if I add 2 to both sides, I find my output, the y value, is going to be 2, take away just a little bit, in fact, 8 and 1/20. So I'm going to reduce that a bit. That's going to be, let's see, they're both even, so that's going to be the same as 4 over 60. They're still both even. That's going to be 2 over 30, which becomes 1 over 15, and that doesn't reduce. So you have 2 take away 1/15, better known as 1 and 14/15. So if you probably guesstimated, if the cube root of 8 is 2, the cube root of 7-ish is probably a bit less than 2. Well, there it is. Hope this helps.